Hi, everyone, and welcome back to another exciting day of AP Physics. Today, we are going to focus on the kinematic formulas, and I'm going to kind of talk to you guys about some tips and tools and tricks and figuring out which equation to use. So when I look at everyone's reflection of our last video, the biggest thing that I am seeing is that everyone is kind of wondering, when do I use which equation? Okay. And there were a couple other questions that came up in that. So hopefully you'll notice that I answered the questions that you asked in our last video. Okay. So we have our major kinematic equations, and one other one that does not include acceleration, but one other one would be our x final equals x initial plus velocity times time. Okay. But these are our major kinematic formulas, okay? And so if we look at them, we have Vx, or our V final, equals V initial x plus Ax t. Then you have this one right here, which I like to rewrite as change in x equals Vx initial t plus 1/2 AT squared. Now, you may have a couple of questions on this. Your first question might be along the lines of, that x initial or the x0 looks kind of interesting. I intentionally copied and pasted this directly from the AP Physics 1 equation sheet because I wanted to make sure that you are familiarizing yourselves with the exact layout of the equations on the equation sheet. Okay. Another question that I have gotten, or another comment that I've gotten from students, is not really understanding what that triangle means. Okay. That triangle, whenever you see that triangle in science or in math, it usually means, it either means heat, but it doesn't mean heat here, like heat added to a chemical equation. In this case, it means change in. Okay, so when I have delta x, it means change in position, which is x final minus x initial. Okay, so this right here, you've seen this equation written like that. So you've seen this equation as Vx squared equals Vx initial squared plus 2a change in x. Okay, so these are our kinematic equations, and one thing that College Board wants to make sure that you know is, if I just give you a question in terms of variables, can you solve the question? So for example, if acceleration is doubled, how much time does it take to change the velocity by the same amount? Okay, so if I'm doubling, so I'm looking at a change in velocity. Change in velocity is equal to acceleration times time. Okay, and I get that from this top equation. So I'm being asked, if I doubled the acceleration, how much time does it take to change the velocity the same amount? Well, if I'm doubling my acceleration, so I have 2 times a, how do I make that equal to the same value of change in v? Well, I would have to have t cut in half. So it's going to actually take half of the time if acceleration is doubled. Okay. Now, if time doubles when an object is dropped from rest, what does that do to the distance it will travel? So one thing I want to point out is, when I'm dropping something, I'm actually changing that in the y direction. So you would change your x variables to your y variables. Okay. And I'm wondering what happens if time doubles. What happens to the distance? So I'm going to use this equation right here. And that equation tells me change in y equals v initial t, but our v initial is 0. So we're just going to cancel that. 1/2 at squared. And we're going to talk about what that a value is later on in this lecture. Okay. And so if I double the time, what does that do to my distance? Well, I have 1/2 a, and then my t is doubled, squared. That's going to end up giving me 4 times 1/2 at squared. Okay, this 1/2 at squared, 1/2 at squared, using substitution, we know that we've changed our y value by 4. Okay, so if I double my time, I quadruple my position change. So looking at some more of these types of questions, I would like for you to look at, okay, which equation are we going to use? So choose which equation you would use to solve each of the following problems below, okay? A car is traveling at 5 meters per second. It accelerates at -1 meters per second squared. So it accelerates for 3 seconds. So I have my v initial, I have an acceleration, and I have a time. What is the final velocity? So I'm trying to find v final. Okay, so I have v initial, v final, acceleration, and time. So I'm going to go back to our equation. Okay, v final, v initial, acceleration, and time. V final, V initial, acceleration, and time. If I were to clear the ink on this slide, I have a V final, V initial, acceleration, and time. So that's going to be the equation that I'm going to use because I'm not throwing in any other variables there. Okay, so in this equation, I'm going to use V final equals V initial plus acceleration times time. Okay. A car is traveling at 10 meters per second, 10 meters per second. It accelerates at -2 meters per second squared for 2 seconds. So I have an acceleration right here. I have a time right there. I also have a v initial right here. And then it says find out how far, that's what we're looking for. So we're looking at our change in x. It traveled during the 2 seconds. So we have a v initial, we have an acceleration, we have a time, and we're looking for change in x. So we have these 4 variables. Notice we do not have a v final. We do not have a v final. So when I go back, I don't want to include anything that has a v final. So I'm not going to include this one, and I'm not going to include this one. I must be needing this equation. So I need my change in x equals v initial t plus 1/2 at squared. Okay, so for this next one, we have a car is traveling at 2 meters per second. So we have a v initial. It speeds up to 10 meters per second over a 4-second period. So we have v final, we have time, and it says how far does it travel? Okay, so we're looking at change in x. Okay, well, if I look at my change in x, I have a change in x equals v initial t plus 1/2 at squared. Okay, the problem with this is that we have a time, but we don't have an acceleration. So we would have to solve for our acceleration, and sometimes we have to use more than one equation. So in that case, we're going to have to use the fact that we know acceleration is change in velocity over time. So you would find the change in velocity over time, and then you would end up plugging that in for your acceleration. Then you have everything else that you need. A car is traveling at 3 meters per second. It accelerates at 2 meters per second squared. So we have v initial, we have acceleration for 6 seconds. So we have time. How far does it travel? How far does it travel over this 6-second interval? So we're looking for change in x. So we have v initial, we have acceleration, we have time, and we're looking for change in x. In this case, I'm going to use my change in x equals v initial t plus 1/2 at squared. The reason that I cannot use the v squared equals v initial squared plus 2a change in x, the reason I cannot use this is because I do not have my v final. I only have my v initial. So this is not a valid equation to use in this case. Now, in this next question, a plane starts at 15 meters per second and accelerates to 200 meters per second, during a period in which it covers 500 meters. What was the acceleration? So we have our v initial, we have a v final, we have a change in x, and we're looking for acceleration. Well, guess what? We just looked at that. We don't have a time, so we can't use anything with time. So we must use v squared equals v initial squared plus 2a times the change in x. Now, if some of you are wondering, well, what happened to the x's down here? So we have x initial, or x final and x initial. Honestly, I don't write them down unless I am looking at things in the x direction and things in the y direction. But even then, I break things into tables for my x motion and my y motion, okay? But on the equation sheet for the AP test, it is important to know that it is written with the x as the subscript. Okay, so now we're going to do a little bit more with the kinematic equations. This question says a blue marble and a red marble are both released at the same time. So they're released at the same time from the top of a ramp. Both marbles roll down the ramp, accelerating at identical constant rates. Okay. After 1 second of rolling, the blue marble's displacement is x blue, and instantaneous speed is v blue. Those are measured. But the red marble's displacement, x red, and instantaneous speed, v red, aren't measured until it has been able to roll for 2 seconds. So basically, what I know is the time for red is equal to 2 times the time for blue. Okay, so what do I know? I know my velocity and I know my time. I know my initial velocity is equal to 0, and I know acceleration is constant. So I know v initial equals 0. I know acceleration is constant, so it's going to be the same for both. Okay, and I need to figure out how velocity, okay, and time are going to end up interacting, or how they're going to look. So it says, how does v red compare to v blue? So I'm looking at the relationship between velocity and time. Okay, well, I know that velocity is equal to v initial plus acceleration times time, and my v initial is 0. So v is equal to acceleration times time. So if this is v blue, then v red is equal to acceleration times 2 time. Therefore, I know that you have 2 times acceleration times time. So v red is 2 times the velocity of v blue. V red equals 2 times the velocity of v blue. Okay. How does x red compare to x blue? Well, in this case, I'm looking at change in x and time, and how are they related? I also know that my v initial is 0. So I'm going to use this equation. Change in x equals v initial t plus 1/2 a t squared. V initial cancels. So now we're looking at how does x compare if I double time? And we've actually already answered this question. So this is the position for blue. The position for red is 1/2 a 2t squared. So we end up getting that to be 4 times 1/2 a t squared. Using substitution, that tells me that change in x for red is equal to 4 times the change in x for blue. So again, sometimes you'll have questions where there aren't even numbers in these questions. And you're going to look at it and you're going to go, well, this is ridiculous. I've always only done questions with numbers in it. But College Board really wants to make sure that you can do it for any variable, any situation. If you can do it for a question with numbers in it, you can do that one specific question. If you can do it for variables, you can do any question. You can do any question with those same variables. And so that's what the goal is for you to be able to do any question. So let's look at this next question, okay? We have a remote control race car starts from rest at a starting line and accelerates at a constant rate along a straight line path. The car is moving at a speed of v when it passes through a location x meters from the starting line. At what location measured relative to the starting line is the car moving at a speed of 3 feet? So we're comparing x and we're comparing v, okay? And we know that it started from rest, v initial is equal to 0, and we have a constant acceleration in both scenarios. So in this case, we're looking at the relationship here, which is v squared equals v initial squared plus 2a times change in x. V initial squared cancels. So you end up getting v squared equals 2a change in x. So in this case, it says at what location measured relative to the starting line is the car moving at 3v. So if I substitute 3v in for v, that's going to be squared. I end up getting 9v squared. Well, then I substitute this in for v squared. So I end up getting 9 times, okay? It's going to be 9 times. So x is going to be 9 times more, okay? Going to the next question, in a trial of an experiment, an object is accelerated at a constant rate for some amount of time, causing the object to move through a displacement of 25 centimeters. The object is stopped and a second identical trial is performed, except the object is accelerated for 4 times as much time. So I'm looking at how position and time are related, because the question is, how far does the object move? Okay. Again, we have started from rest, so velocity initial is 0, and we have that our acceleration is constant in both scenarios. So in this case, we're looking at position, and we're looking at time, and then we're also looking at acceleration, accelerated motion, position, and time. So we're looking at change in x equals v initial t plus 1/2 a t squared. So it says the object is stopped and a second trial is performed, except the object is accelerated for 4 times as much time. So if I have 4 times as much time, okay, I'm going to have, this is going to cancel. So then I end up having 1/2 a 4t squared, okay? And that's going to end up giving me 16 times 1/2 a t squared, okay? And this is x2. Well, if you looked at x1, x1 is 25 centimeters. Therefore, x2 is 16 times 25 centimeters. which ends up giving me a value of 400 centimeters. Okay, so hopefully that is starting to make sense. If I adjust the variables and I know how to adjust the variables and what the results are going to be as I adjust the variables, then I'm able to show a deeper understanding of the physics. A toy train is released to roll down an inclined track at a constant acceleration rate a, and it is moving at 3 meters per second. As it reaches the end of the track, after rolling for an amount of time t, then the train is placed on a new incline track that is longer and angled more steeply than the first track. So on this new track, the train accelerates at a rate of 2a. So I'm looking at acceleration changing now, and it rolls for time 2t. So I'm relating acceleration, time, and then it says, what is the train's speed? So I'm looking at how velocity, acceleration, and time are related, and I know v initial is equal to 0. So if I think about that, I am going to relate those. Well, how do they relate? V equals v initial plus acceleration times time. Okay, so if I'm looking at that, then I know my v initial is 0. Okay, so my v, we're looking at acceleration. Okay, and we're looking at time. So we've done 2a and we've done 2t. So how much have I changed that? I've changed that a value of 4 times AT. Okay, so the new speed is going to be 4 times the initial speed, the initial situation. Okay, so in this case, I end up having 4 times our first, which is going to be 3 meters per second. And so 3 meters per second, we have 4 times 3, we're looking at 12 meters per second. Okay. Okay, so now we're going to move into our last topic for 1D motion. Notice I have stayed with our x values. We're moving in the x direction. We've been moving left and right all week. Left and right, left and right, left and right. I've mentioned that we can go up and down, but I have not talked to you about what that motion looks like up and down. Now, when you think about something, like say I drop the ball, something is going to cause that ball to drop. What is it that causes that ball to drop? That ball is caused to drop by gravity. There is a gravitational force that's pulling that ball towards the center of the earth. So free fall is the vertical motion of an object in the presence of only gravity. The vertical motion of an object in the presence of only gravity. On Earth, all free fall objects accelerate downwards at a rate of 9.8 meters per second squared. Now notice I said on Earth. Gravity, the force of gravity, is different on different celestial objects, right? And we'll talk about that more in this semester, in this quarter. But I want you to understand that it's only on Earth that we're at 9.8 meters per second squared. So as you look at this object being thrown up in the air by this person, you have gravity acting down at, we're going to make down negative 9.8 meters per second squared. Now, if you're sitting there thinking, wait a second, over there you have positive. Yeah, I'm just saying that it's facing downward at 9.8 meters per second squared. So then at 1 second, you have your acceleration is negative 9.8 meters per second squared. Up here at your 3 seconds, your velocity is 0. Does that mean that your acceleration is 0? And my answer to that is no, because if your acceleration is 0, then that ball is just going to suspend in air there. So up at the very top there, your velocity might be equal to 0, but acceleration is still pushing it down at a rate of 9.8 meters per second squared. It's working against the motion of the ball. So going up, it's slowing down. because your velocity and your acceleration are opposite directions. Coming down, it's speeding up. Now, something that I think is really cool and really important is you're going to be at the same, so at the same distance, your velocity is the same. It's just one's going up and one's going down. At the same distance horizontally, your velocity is the same, except for one's positive going up, one's negative going down, okay? And then right here, again, same distance, velocity is the same. So at the same exact horizontal distance, your Vy is the same. At the same exact horizontal distance, your Vy, or your velocity in the y direction, is exactly the same. So when you're looking at it at a level playing field, your velocity up and your velocity down is going to be the same. It's just going to be equal magnitude, opposite direction. Now, here's a common misconception. A lot of people think that things that are heavier will fall faster, and that's actually not true. It's not true at all. More massive objects will only fall faster if there is an appreciable amount of air resistance. So if there is a lot of air resistance, that's going to be a different story. However, in this case, when we're looking at just a baseball or whatever, if you look at it in terms of a vacuum, then both objects, no matter what their mass is, will fall at the same rate of 9.8 meters per second squared. Now, here are some tips in problem solving using these situations. Number one, always use your kinematic formulas. Number two, your acceleration in the y direction is always equal to gravity unless otherwise stated. Your acceleration in your x direction is equal to nothing unless otherwise stated, unless you're given a question about acceleration in x. Whatever you choose as your positive and negative matters. For example, I can make my top positive y and my bottom negative y. Or I could flip it, and I could make my bottom positive y and my top negative y. But if I have a vector going up, then I need to make sure I use negative. If I have it going down, I need to use positive, okay? Now, this is something that's best explained in class, so it's something that we can talk about. And then upward and downward halves of motion are symmetric, and that's what I mean by this, at the same horizontal position. And then also time, too. So when I have a projectile, so like the time up, in this case, is equal to the time down. The time up is equal to the time down. Notice you go 0, 1, 2, 3 seconds. 1, 2, 3 seconds down, okay? X is equal to 0, or your change in X is equal to 0 if you start and end at the same height. V is equal to 0. Your V final is equal to 0 if you are going to the maximum height. So at your maximum height right here, your V final equals 0, but that's only in your X direction, or I'm sorry, that's only in your Y direction. I need to make sure that you understand, you know that, because your Vx is not going to change, and we'll talk about that next week. V initial is equal to 0 when it is dropped from rest. Okay, so if this person right here, instead of throwing it up, is just going to hold it out, hold the ball out, and then it's just going to drop, your V initial at that point is going to be equal to 0. Okay, so moving on to a couple of sample problems. A student in an experiment wishes to determine the unknown constant acceleration that is occurring for a ball rolling down an incline. So wants to know the constant acceleration. Measurements are taken at several points along the ball's motion down the incline. For the ball's position along the incline, measured relative to its starting position, and also its rolling time, relative to the time it started rolling. Data from the experiment. So this whole started rolling, it's important to see that it started, your initial velocity is 0. Data from the experiment is shown. What quantities should be graphed so that the best fit line accurately fits the data points? So what you want to do is you want to figure out what value with position and time will the graph give me acceleration. So if I have position divided by time, I want that to give me acceleration. I'm not saying it gives me acceleration. What I want to do is I want to figure out what would I have to do? What would I have to do to figure this out? Okay. And so what I'm going to do is I'm going to look at my kinematic equations, and I know a kinematic equation that I can use is change in x is v initial t plus 1/2 a t squared. My v initial is 0. So I have change in x equals 1/2 a t squared. And I now want to get acceleration by itself. So acceleration is equal to 2 times change in x divided by t squared. So if I made this my y value and this my x value, then I should be able to get my slope. So I want to graph a graph of 2 times change in x versus a t squared graph. So then it says fill in one or both of the blank columns. Now, I really want to stop for a second and tell you this is very common. This is a very common type of AP Physics problem, because you're being asked to look at the data and say, okay, how can I manipulate and change the data to give what I want? Okay, not change the data like changing the numbers, but how can I manipulate it and shift it so that I'm going to get a constant slope? Okay, I'm going to get my best fit line, and I'm going to get a constant slope that's going to give me my acceleration. So I've already calculated my 2 times change in x, and I've calculated my t squared. So I'm going to go ahead and plug those in. I have 0, I have 0.36, then I have 0.81, 2.25, and 4.41. And then over here, I have 0, 1.0, 2.4, 6.8, and 12.0. Okay? And then I'm going to go ahead and graph those values. So I have them written down on a piece of paper next to me. So I'm going to go ahead and graph these values. Okay? And I am going to graph as if this was 2, 4, I want to choose a consistent 6, 8, 10, and 12. Now you shouldn't probably go all the way up to the top, but it really worked best for me. And this is labeled 2 times change in x, which is my meters. And then this right here, down here, I have 1, 2, 3, 4, 5, 6. And this is my time squared, which is going to be a second squared. And when I end up graphing that, I end up getting something that looks like something that looks similar to this. So we've got, in the end, 4.41, 4.41 and 12. So I'm up here. And then when I end up finding my best fit line, okay, and I actually ended up bringing mine through 0. And when I end up finding my slope of my line, okay, which I could even take even this point right here. So then that's going to be 3.4 is my x, 3.4 We'll say minus 1. And then I have 2, 3, we'll say 3.2-ish. And then this is going to give me about 8, 9, 9.5-ish, or 9.4, we'll say. And I used different data in what I had, okay? But this is going to be 6.2 divided by 2.4. And if I looked at that, I actually used 6 divided by 2.2, and I end up getting somewhere around 2.7 meters per second squared, okay? So that's how you would graph something like this. That's how you would graph this type of question, okay? Now, looking at question number 19, it says a ball is kicked straight up in the air from ground level, upward from ground level at a speed of 15 meters per second at a time of t equals 0 seconds, neglecting any effects of air resistance. At what time does the ball reach its highest point? At what time does the ball reach its highest point? So we're looking at time. We know acceleration is going to be downward, negative 9.8 meters per second squared. We know V initial is equal to 15 meters per second. And it says at our highest point, V is equal to 0 meters per second. So we're looking for time in this case. We're going to use the equation V equals V initial plus acceleration times time. Okay, so V minus V initial divided by acceleration equals time. When I go ahead and plug that in, I get 0 minus 15 meters per second divided by negative 9.8 meters per second squared, and that gives me 1.53 seconds. Now, those of you guys who have seen before, you guys have seen us do the rocket labs. This is like what we would do for the rocket labs in figuring out maybe our initial velocity, okay? At what time does the ball land back at ground level? At what time does the ball land back at ground level? So we're looking for time, okay? We have our initial velocity of 15 meters per second. We have our acceleration is negative 9.8 meters per second squared. And our change in x is actually, or change, we'll say change in y, I apologize, is actually equal to 0. So we have change in y equals v initial t plus 1/2 a t squared. Okay, 0 is equal to 15t plus negative 4.9 t squared. Well, one of your t's is going to cancel because that's going to be 0. Time equals 0. That's why you have two values. And then t equals 3.1 seconds. At what time does the ball pass through a point 2.3 meters above the ground? So we're looking for time. V initial equals 15 meters per second. A is equal to negative 9.8 meters per second squared. X, or I'm sorry, change in y again, is equal to 2.3 meters. So when we look at that, we use the same equation, change in y equals v initial t plus 1/2 a t squared. So we have 2.3 equals 15t minus 4.9t. Well, dang it, what do we use? we use your quadratic formula. Where your x value is your t, and in that, for the sake of time, we end up finding 0.16 seconds and 2.9 seconds. Again, why is there 2 times? Well, because at this point, we're 2.3 meters above the launch height, okay? So we have 2 different points. We have a time here, time going up, and a time going down. And then our very last question for actually for this section for 1D motion is going to be: a rock is launched straight downward from a cliff at 18 meters per second. So here's our cliff, and we have taken this rock, and now you have an initial velocity of 18 meters per second. How fast is the rock moving when it reaches a point 5 meters below the initial launch position? So change in y equals 5 meters. So I have talked to you already about switching my axes. And here's the thing. In this case, I'm going to do that because everything is directed down. And if I set everything with negative numbers, I tend to lose my values. So this is my negative going down, and going up is my positive. So what I did is I set my So what I do, because everything is going down, is I set my down as being positive and my up as being negative, because I have nothing going up. So now I have my V initial, okay? I have my change in y, and I have my 9.8 meters per second squared is my acceleration, and it's the same, it's in that positive direction, or what I've set as my positive direction. Now, the question says, how fast is the rock moving? So I'm looking for V final, okay? In this case, I'm going to use V final squared equals V initial squared plus 2 times A times change in y. V final is equal to the square root of V initial, which is 18 meters per second, squared plus 2 times 9.8 meters per second squared times 5 meters. Okay, and when I calculate all of that out, I end up getting the square root of 422, which ends up giving me that my velocity is 21 meters per second down, or you can write negative 21 meters per second. Okay. So you guys, that's all for our notes for today and for 1D motion. I know that that was long. Sometimes it just gets kind of grueling, but it's really important that you use these in-class practice problems to help you solve the problems. And if you're not able to answer the problems after you've used the in-class practice problems and after you've used the videos, then please reach out to a peer and then reach out to me, okay? I want to help you. I want to get you guys going and ready to go for any assessments that come up, but also I want you just to understand the physics and the physics of motion. So again, if you have any questions, go ahead and reach out and we'll connect soon.